is positive because it contains protons. Now you should know, because this was a nucleus which contains protons plus neutrons. Neutron has no charge, so it means overall nucleus is positive. So how small is electric charge? For this, I have told you yesterday the whole story, that how that scientist got this value, minus 1.6 times. Like here, this minus 19 is in the power, like this, 10 raised to power minus 19. It means this much small one electron is. So how small electric charge is? Charge on one electron. Charge on one electron is this much small, and this is extremely small. Obviously, this is 0.000000, like 19 zeros, and then it's 1 6. So this is extremely small. And proton has exactly same charge but positive sign. That's why overall atom is neutral. Now about 606 multiplied by 18 electrons are needed for 1 coulomb. It means 1 coulomb is equals to 6 multiplied by 10 raised to power 18 electrons. After that, coulomb is very large unit. Next question which comes is that why are most objects neutral? What's the reason of they're neutral? So neutral means equal number of protons and electrons. That's what neutral means. And neutral has no charge overall. Now, this is not the answer, obviously. Why are most objects neutral? So atoms, let's take the example about atom. That atom with 6 protons and 6 electrons. It means positive is equals to negative. It means the total net charge will be equals to 0. When there is no movement, it means there are equal number of protons, equal number of electrons. So the total, like on one side is positive, on the other side is negative, and it's gonna be the net charge which will be equals to 0. There will be no charge. That's why most objects don't shock us all the time, because they are neutral. It means they haven't been rubbed with some opposite object, or that's why they are not giving you the shock. That's the only reason, because they are neutral. Now, moving toward electric fields. The more about electric fields. Before, I had given you the small concept of electric fields, that because of electric fields, these things are happening here. Okay, let's take, here I have told you what electric field is, that the region around a charged object where force acts. That's what electric field is. Now I'm giving you more clear idea of electric field. So here is the electric field. You have to listen to it very carefully. This is an important topic to remember. So the region around a charged object where it can exert a force on an other charge. See, this is the charged object, for example. This is a charged object. The region where it exerts force on an other charged object is named as electric field. The region around the charged object, there's some object here. Like this is okay, take it as ruler. Wait, let me draw it. This is the object. So region around this charged object is named as electric field because it can exert force on another charge. Important idea is there's no touching needed. Force acts at a distance. Like there's no need that both objects are touching. See, even the ruler is at a distance, still it's pushing the small pieces of paper towards it. Like it's not even touching. They are in the air. So that's what the property of electric field is, that between that area there's electric field which is acting, because of which that push is occurring. So an electric field, the region around a charged object where it can exert a force on another charge. Important idea, no touching needed, force acts at a distance. Let's move toward example. Example is charged comb attracts paper bits. It means that comb does not touch the paper. I already told you that why that ruler is not, like without touching, it's attracting those pieces of papers. In the same way, charged comb attracts paper bits because comb does not touch the paper. Electric field does work there between those comb and the paper bits. Now let's move toward, why do we draw electric field lines? electric field lines are even invisible. Like if you see that when this attraction is happening, like the charge from attracting the paper bits, there is no electric field lines visible. But scientists draw these lines to show the direction, that what's the direction of these electric field lines, that why the one has the more ability to attract and one becomes positively charged, the other becomes negatively charged. To show this, scientists have drawn the lines, electric field lines, to show the direction, strength, and shape of the field. Now, what is the shape of that electric field is? So for this, you should remember these key rules for electric field lines. Rules for electric field lines is line go out of positive charges. See, if you see, these are the positive charges, right? The lines go out of these positive charges. This is the key rule for electric field lines, and lines go into negative charges. See, if it's a negative charges, the arrows are inward. So for negative charges, lines go inward into the negative charges, and lines never cross. See, are these lines crossing each other? No. See, they are far apart. This is the second rule to remember. And then its direction shows force on a positive charge. Always imagine. Here, let me tell you one thing, that why we always imagine a positive test charge like this positive test charge. Why we always imagine positive? So the simple reason for this is, it's a simple possible situation to understand an electric field. Think like this, that before learning two charges, plates, and complex shapes, we must first understand how one single charge affects the space around it. What does isolated means? So isolated means only one charge. See, isolated means only one charge. Okay, and we are taking isolated positive charge. It means only one charge, no other charge nearby, no external influence. So the effect we see is purely due to one charge. That's why we are taking, see, I have written here that always imagine the positive test charge here, because it's only one charge and no other charges nearby. It means no external influence. So the effect we see is purely due to one charge. Let's move toward why specifically a positive charge. Because electric field direction is defined using a positive test charge. If I place a tiny positive charge near this charge, which is why it will move, this gives a standard reference, because when it was being discovered, at that time, the positive charge was being taken as the reference. So that's why we take it as standard reference. And we always prefer to imagine this one, a positive test charge. Let's move toward that. What do students learn from this case? From an isolated positive charge, they learn that electric field spreads in all the directions like this. The electric field spreads in all the directions, and field lines go outward because it's positive, and strength is strongest near the charge and weakens with the distance. See, near the charge, the strength is the strongest, and it get weakens if the distance between two charges is too much. As already told you, that relationship between them, that how it weakens, and what's the effect of distance. Let's move toward that a charge does not need contact to exert force. I already told you that they are already, like if there are two charges, there are two objects are distant, they are still exerting the forces. There is no need to touch them. Okay, if they are like charges, they're going to repel, and if they are opposite charges, they're going to attract. It means they don't need contact to exert force. It affects the space around it. This idea is the foundation of electric field. Now let's take the case of two parallel plates. Here, the case of two parallel plates. What are two parallel plates? These are the two parallel plates. Like one plate is positively charged, other plate is negatively charged. Plates are flat, parallel, and very close compared to their size. They are that much close compared to their size. Okay, now positive plate pushes positive charges away, right? And negative plate pulls positive charges toward itself. That's what happens. That the positive charges in this plate are repelling and this negative plate is attracting. The next thing happens here is that so a positive test charge placed between the plates feels pushed from positive plate. Now these were the two plates, right? Now the positive test charge were being placed between these two plates like this. And what happened here is this was the negative plate and this was the positive plate. So this positive test charge, what force this positive charge exerted was that from this positive charge it gets repulsion because they are same, and while from negative charge the attraction occurs because of the opposite charges. So from positive charge it feels push and from negative charge it feels the pull. So both forces acts in the same direction. Let's move towards uniform electric field. What uniform electric field is? Plates are large and parallel. Distance between them is small. Field lines do not spread. Okay, let's conclude whatever we have learned till now by the real life example of comb and hair with the tapers, like these pieces of papers. So you have to first rub the comb with the dry hair. When you bring it near to the small pieces, that these small pieces of paper jump toward the comb. So the comb attracts paper without touching it. That's what you concluded from this point. That when you rub this comb and when you bring it close to these paper pieces jump toward the comb. Okay. The next step is that how does the comb pull paper without even contact? You just bring it close. The both of them are not in contact, but still these paper are jumping toward the comb. What is the reason? So there must be something acting between them, right? That's why this jump is happening. So for this, you should know about electric field because this is the electric field because of which this thing is happening. What electric field is? You already know the definition of electric field previously, that electric field is a region around a charged object where it can exert force. Around a charged object. See, here the charged object is comb because when you rub it with the hair, it becomes charged. It means it becomes negatively charged. It's acting like a negative charge. Now, paper is neutral. This paper is neutral, right? Like it's having both equal number of positive and negative charges, right? Now, what's going to happen? This is paper and this is the comb. This is the comb. Okay? So, the comb is negatively charged because you have rubbed it, and the paper is neutral because it's having equal number of positive and negative charges. So, charges inside the paper rearrange when you see, before they were random, like this, positive here, there, and they were very random. When you bring this charged object close to this neutral object, these will rearrange. Like the positive will on the one side and negative becomes collected on the other side when you bring the charged object closer to it. Now positive charge move closer and negative charge move away. Because charged object is negative, it means negative charges will repel of the paper while positive charges come closer to that charged object because they are opposite charges. You have to keep this thing in mind. Now, next thing to notice is the electric field pulls the paper toward the comb. So this is the electric field which is pulling toward. See, you already know from this diagram that if this is a positive charge, right, and this is a negative charge, when you bring close like this comb, when you bring it close toward this, these force act inverse, right? It means the electric field pulls the paper toward the comb because this was the comb, right? So the electric field pulls the paper and this was the paper and the positive charges from the paper were coming work the cause of the attraction because opposite charges attract each other. So the electric field pulls the paper towards the comb like this. Now let me tell you that this is non-uniform electric field. Because if you see here, there's a small distance and that distance is different in these electric fields. But let me tell you about uniform electric field. A uniform electric field is when the distance is same. Like these, the distance should be same, then it's gonna be the uniform electricity field. But for this comb and paper example, the electric field is non-uniform because these field lines are at this different distances and their strength is when the comb is little far away, the field gonna be weak, and when it's close, the field gonna be strong. Okay, the last step to tell you about uniform electric field. Uniform electric field exists between two parallel plates. One is positively charged, other is negatively charged, and between them the field gonna be straight with equal distance. So this field is known as uniform electric field, which will move from positive towards negative because I already told you that from positive the field lines are outward while in negative the field lines are inward. That's it for today. If you have any question, you can ask.